Hello guys and welcome back to another YouTube video on object code generation for a SIC/XC program. So moving ahead, this is our program. You can see we have the content, and what we have to do is to write the object program, that is to write the header record, text record and end record. So for each statement, clearly indicate the instruction format and addressing mode, and for each statement clearly write opcode, addressing modes and displacement/address. Moving ahead, we have our program right here. So what we'll do now is generate the location counter values. And basics, you got to know the four types of instruction formats. We have type 1, type 2, type 3, type 4. So type 1 takes 1 byte, type 2 takes 2 byte, 3 byte, 4 and 4 byte. Now starting, we can see sum right here. So sum start 3000. So this is our starting address. This is where our program starts. So this goes right here. Now we have another instruction right here. It says clear X, right? So X right here is a register. So when a register is being used in an instruction, it's type 2. So what we do is we add 2 to the location counter value. So the current location counter value. Now we get 3002. So moving ahead, we have LDA #0. So this is, if you can see or if you know, is of type 3. The instruction format is of type 3. So type 3 occupies 3 bytes of space. So now what we'll do is the current location counter value is 3002. So we add 3 here. So 3 bytes we add, and once we do that, we get the next one, 3005. So at 3005, we have plus LDB #total. So this plus, it represents that type 4 instruction format is being used. So type 4 takes up 4 bytes of space. Now what we do is we take the current location counter value and add 4. That is 4 to this. Now we get the next one, 3009. So note that this thing, what we are doing is 1, 2, 3. We're adding this is in hexadecimal hex. You just need to know that the values right here are in hex. Now you may also notice that I'm not writing any value right here, because this right here is an assembler directive. It's basically an instruction to the assembler. Now moving ahead, it's not for the program to be converted into object code. At 3009, the location counter, we have add table, X. So this right here is of type 3 because we don't have a hash right here, or no registers are being used. So as a result, it occupies 3 bytes of space. So now we add 3 right here to the current location counter value. So it points right here, 3000C. See, I'm telling you, these are hexadecimal values. That is to be noted. Now we have TIX count. TIX count is again a type 3 instruction format. So it takes up 3 bytes of space. So 3 bytes we add right here to the current location counter value. It points to the next value. So 3000F. JLT. So again, JLT is type 3, no hash, so it's type 3, no register being used, so type 3. This also occupies 3 bytes. We add 3 right here. Next value is 3012. 3012. Shouldn't say 3012, should say 3012. Now STA total. STA again, if you can notice, is type 3. We don't have a hash right here, no registers being used. So as a result, type 3. So type 3 takes up 3 bytes. We add 3 to this again. So next value, 3015. And at 3015, something happens. You can see RESW. We're using RESW right here. We are reserving a word. How many? One word basically. So one word occupies 3 bytes of space. Now what we do is we take in this value 3015 and we add 3 because we are reserving one word. So one word occupies 3 bytes. So we are incrementing the location counter value, the current location counter value, by 3. So that points to 3018. Now at 3018, you can see something happening. So we're using RESW to reserve 2000 words. So as you know, one word is 3 bytes. So 2000 word is not almost, it is 6000 bytes in decimal. Now It's in decimal, so we need to convert it into a hex. You might not know, you might be thinking, wait, we're using 1 2 3 4, we're just adding, right? 1 2 3 4, so 0 to 9, same representation, and then after 9 it changes to A, B, C, goes on till F, right? So that is the reason. But 6000, you need to convert it into hex. So now we are at 3018, right? So we are getting values of 6000 byte. We need to reserve 6000 byte in memory. So we need to increment 3018 by 6000 bytes. How is that done? So we convert this into hexadecimal. We get 101770. What we do now is we take 3018, that is the current location counter value, and we add it with 1770. So see, this is the current location, current LOCCTR, location counter value. So we add 1770. We get a new value 4788, and that is right here 4788. If you can see, now again we have RESW, and 1. So one word is what we're reserving. That takes up 3 bytes. So we increment this by 3 and we get the next location counter value. And now at 478B we have end. So that's basically the end of your program. And we have location counter values. So now you understood how location counter values are generated. So we generated them successfully. And now we'll be using this to generate some object code. So we'll be filling in object codes right here. Now, start 3000, not really needed. So the first instruction that we, come into, or we see right here, is clear X. So if you just notice here, and if you know all the formats, clear and X register is being used right here. So this is of format 2 or type 2. So this takes up how many bytes? 2 bytes. And how is that bytes, split in? So here 8 bits, 4 bits here, and 4 bits here. These are the registers being used. For now we can see X, there's only one register being used, so we'll just take R1, and R2 will keep it as 0000. Now X, we have the table for all the registers right here. So X, you can see it's 1. So if you convert 1 into binary, it's 0001, and we fill in that value right here. Now then we have clear right here. This is the instruction, right? So instruction clear is B4. This is the mnemonic value. This will be given with your question, most probably, or you can just refer and get the value of what clear means. So it's B4. So this is B and this is 4, right? 4 and this is B. So once you convert B4, which is in hex, to binary, we get this value. So this value is fed in right here, clear opcode, and then register R1, that is X, we are using 0001, and R2 0000. We're not using R2. So now how do we generate the object code? So this whole thing should be in hexadecimal representation. So we'll split 4 4 4 4 4 bits, 4 bits. Now this is what? This is B, we know that. This is what again? This is 4, and this is 1, and this is 0. So we get, if you combine all of that, you get B, 4, 1, and 0. And that exactly is your object code for the first instruction. Moving ahead, we have LDA, right? Now we can see you have something right here, the hash. This indicates that this is immediate addressing. So we just need 0 into the memory immediately. Now what we do is, as you know, there is no registers being used. So format 3 takes up how many? 3 bytes. So first we look into the opcode. So opcode LDA is represented by 00. 00 is 1 2 3 4. That's for the first 0, and the second 0 right here. Now this takes up only 6 bits. So how do we fill it? We have LDA right here we have 8 bits right here. Like in the previous instruction, you can just take this and just put it in right there, all the 8 bits. Now what we do is we only take the significant 6 bits right here. This one, these. We take only till these and fill it right here. Now you can see 1, 2, 3, 4, 5, 6. These significant 6 bits. And next, NIX BPA. These are some flags you need to know. Now we are using immediate, right? So you take this and put it right there. So we'll set this to 1, set this high. And then all of these we'll look into. For now it's 0. And displacement. There is no displacement, right? There is no displacement we are taking into consideration. And displacement, by the way, takes up 12 bits of space. That you can see 12 bits. So for now, we'll generate the object code. It'll be, see, I've split the 6 significant bits into 4. So this 4, and then here, and then these 4, 4, 4, and there you go. And each of these you represent. So this will give you 0. This again is 1. This 0. And this is 0 again, 0, and 0. Right? So if you combine all of this, you get 0, 1, 0, 0, 0, 0. And that exactly is your object code. Moving ahead, we have plus LDB, hashtag total. Hashtag, wow, hash total. Okay. So this plus represents a format 4 instruction or a type 4 instruction, which takes up 4 bytes. Now, as usual, this is 6 bits, right? We have all of our flags right here, and then we have this space right here. This is 20 bits. We take in the address. Before, in format 3, we were taking displacement, right? But now we'll take in the address directly. And note that this is of 20 bits. Previously, the displacement was of 12 bits. Now, moving ahead, we have LDB, right? So LDB is represented by 68. I shouldn't say 68, it's 68. So 6 and 8. 6 and 8. So I'll split the most significant 6 bits, that is these, and fill it right here in the opcode space. There you go. Now here I've separated the first 4 for better understanding. And E, extended, extra. So we're using format 4. Whenever we use format 4, this bit will always be high. And you can see in the previous one, extended is 0 because we're using a type 3. But here we're using type 4. So that is 1. Now, moving ahead, hash total. So immediate, that is high. And address, 20 bits. How are we getting this address? Right? We're not getting displacement, we're getting an address directly. So you can see here, hash total. So where is hash total? If you come down here, there is total right here. And what is the address? We have 4788, right? You take this and directly put it in the address field right here. So this is 4 bits, 4, 4, 4, and 4. So you can see right here. So 20 bits representation, each of this value 4 bits, 4, 4, 4, 4. So 3, 4, 5. 4 5 are 20. So now we can generate the object code successfully. So grouping, by grouping 4, 4, 4 right there, and the next 4 right here, the next 4 right here, and this as well, you can take it in the same way because this is hexadecimal representation. It'll be easier for you guys. So 0, 1, 1, 0. 0, 1, 1, 0 is 6, and right here we get 9. So this is 1, and this you can take it as it is. So combining all of it, we get 6, 9, 1, the 0, 4, 7, 8, 8, and that exactly is your object code. Now moving ahead, we have something different right here. So you can see base and total, it says right here. This will not generate any object code because it's an assembler directive. So we don't generate any object code for assembler directives. Then the next instruction right here, it says add table comma x. So here x you can see this basically is displacement, you can indexed or displacement basically. Now calculating the object code, we have add. So add is represented by 1 8, 1 and 8, 1 and 8, right? And the most significant 6 bits are these, and those will be represented right here in the opcode field. Now next, NIX BPE. We have 1 and 1 here because we are not using those, N and I. simple, and then X. So you can see 1 and 1 here because we are not using an I, and then X is 1 because we are using an index. So once we have that, B is 0, P will come to Y, it's 1, and D extended is 0 because we're using a type 3, which is of 3 bytes. And displacement will calculate. Now, displacement is something you need to calculate always. 3018. Now, how do we calculate displacement? You can see add table comma X. So add is right here, and you can see 3018 minus 300C. The instruction now location counter will be right here. It will execute this and be right here. Current value, right? It's pointing at 300C. And then table, the value of table is stored where? You can see it's stored here, 3018. So what we do is calculate the displacement from here to here. That is done using this. So 3018 minus 300C. We got 000C. And we need to fit in only 12 bits. This is 4, 4, 4, and 4, right? So only these we need to take. That gives 12 bits. So we take this value and fit it right there. And also you need to see. So to use program counter relative addressing mode, that is this thing, we need to see whether that the displacement that you get, the value, fits in between these values. That is minus 2048 to positive 2048. If it fits in, then you're good to go. You can use the program counter relative addressing mode, and then we take in the 12 bits right here. We put it right here. Now you've got all your values, grouping 4, and then 4, then 4, and then you can use as it is because this is X. Now 0001 produces 1, 1011 is B in hex, and 1010 is 10, that is A. So combining all of this, you get 1B A 00C, and that exactly is your object code. So next one, we have TIX of count. Now again, TIX and count, you can see is a format 3. There is no registers exactly being used, and then there is no plus right there to say it's extended. So 3 bytes. And TIX, if you see or if you refer, it's given as 2C. So 2 is this thing and C is this thing. So the most significant 6 bits you take and feed it right here in the opcode field, and N and I 11, simple, and then X 0, there is no indexing, and then P is 1, E is 0 because there is no, it's not extended, right? It's type 3, and then displacement. So Y1 right here again, we'll calculate that by the displacement. Now we calculate displacement. TIX, the value, the location counter value is right here. It's at 300F, right next after this. And then count. Where is count? You can see the label says count right here, right? Count. And the address is 3015. Now we need to calculate the displacement right here, this displacement. And that is done by 3015 minus 300F produces 0006. So again, we are getting more number of bits, and then we need to take only these. This is 4 bits and 4 bits representation, right? So this produces 12. So 12 bits we take and feed it right here. And before that, we also check whether 0006 or 006 lies in between these values. And if it does, then only use program counter relative addressing mode. And obviously 006 does fall in this range. So we'll just feed it right here, 006. This is X value. You need to remember. So this is 4 bits, 4, 4, right? So together they give 12 bits. And now to generate the object code, we'll start grouping them into 4. So I've given a space right there for your better understanding. 000, 0010, and then again 4 right here, 4 right here. So now what does this produce? So this produces 2. So 1111 all 1. So it's F. And this thing is again 2, right? 0010. Now grouping all of this, get 2F, 2, 0, 0, and 6. And that exactly is your object code. Moving ahead, next instruction, JLT of loop. So again, you can see there is no plus right here, so it's format 3 bytes of space. And then again, JLT has value of 38. So converting this into binary, we have 3 producing this thing and 8, 1, 0, 0, 0. There you go. Now the most significant 6 bits, these are fed into the opcode field right here. So again, you can see n is 1, I is 1, so simple. X 0, B is 0, P is 1. We'll look into that. So first you calculate displacement and then you feed in values right here and type 3. So you can already decide this will be 0. Now displacement will calculate. It says JLT. So this is your current location counter value. And then loop. So where is the label loop? Label loop is right here. And the value right here is 3009. So we need to calculate this displacement. And for sure, it will be negative because it's going up. So 3009, that's the destination, minus 3012, your current value. It gives minus of 9. So what we do right here is, so you take this, convert it into 2's complement, and then get your hexadecimal value. Or if you're using a calculator, you can change it to hex and then directly do this operation. You get this value directly. So it's FF7. So we take the last 3 bits, or last 3 values, that this is of 4 bit, of 4 bit, 4 bit. So 12 bits displacement we got. This thing is in hexadecimal and it lies obviously in between these values. So that's very important. So it does. If you convert these, you can see it does value. Okay, or you can just check right here, minus 9. Obviously it does fall into this, right? It's in between these values. So you can take, yeah, it's program counter relative. And this value can be fed directly into here. So 12 bits displacement. Now, once all the fields are used, now you can see you can put 1 right here because we're using program counter relative, and B 0. There's no base relative. So now we'll do grouping. 4 right there, 4 right here, 4, and this you can use as it is because it's hex. So we need to generate object code which is hexadecimal. Then now we convert this into hex now. That's 3. So if you convert this, it's B, and that's 2. 2 is 2 in hex. And then you can just combine it with these values and get the object code. So that's 3B2 FF7. And that exactly is your object code. The next one. Now it gets a bit tricky right here. So we have STA and total. So the instruction is STA, right? STA represented by 0C. So 0, you have your 4 zeros, and C, and you have this value. So the 6 most significant bits, these are, and they will be fed right into the opcode space. Now that's done. You got your opcode thing and all of that. NIX BP, you'll feed it right here, and this thing obviously you can set by yourself 1 1 0 because simple. And then B, we'll look into this. Don't set any of these and extend it 0 because we're using format 3. Takes up 3 bytes, and displacement will calculate. Now you can see STA. So your location counter values 3015 for now, and then it says total. So we go searching for the label total. So total is right here, and this is 4788. This is your address of total. So we need to calculate this displacement, right? Now calculating the displacement, we get 4788 minus 3015. We get 1773. So this is in hex, right? So we need to convert it into decimal. We get 6003 in decimal. So 6003, if you know, is basically greater than all of this, right? It does not fall into this value. It's more. And the other part is that you can see the displacement produced here. So displacement needs 12 bits, right? Here you can see how many bits displacement. That's 4, 8, 12, and that's more than 12 bits. You need these, but that's not displacement, what you're getting. So that's something. It's producing a 16-bit displacement. Now, as we know, it is falling outside this value. So the displacement is falling outside this value. So you'll rule out program counter. You're not using program counter. You're using something called as base relative address invert. So you'll use your base register. That is, so the displacement. Now we'll go back to your program. So where is the base register? So this is your base register, right? So base and total. What is it holding? It says total. Now what we do is effective address minus base will give you a displacement. This is known, I guess. It's same for program counter, but instead of base we have your program counter value. So now effective address is your address of total. So what is the address of total right here? So total is 4788, right? So effective address 4788, that's this thing. And what is the value of your base register? So base register, again, if you see right here in your code, is holding total. So going to the total label is again 4788 right here. So 4788 minus 4788. So that gives you zeros. So 3 zeros because 12 its displacement, that's 4 plus 4 plus 4. Excuse me for that. Okay. So this thing, you'll feed it right here. And now you can see we're not using program counter. So that goes 0. And then we're using base. So that's 1 for that. Now grouping, you have all of your values right here. You can group it into 4s right there and right there. And this you can use it as it is because it's hex. Now we have this thing 0 0 1 1. That's 3. And this thing produces B. This thing is 4. And this thing you can use it as it is. So combining all of that, you get 3B 4 0 0 0. And that exactly is your opcode right here. Then moving ahead, you can see RESW are assembler directives. So I said before, we are not generating any object code for assembler directives, right? And then we have end, which is another one. So I'm just filling in the starting address of the program, and note that this thing is not an object code right here. This is only for a reference right here. We're just filling in the starting address, which is 3000. It's given right here. So this value I'll just copy and put it right here, and you'll see why we'll do that. Now we have all our object code right here, and then now we'll make the object program. How do we do that? We use the header record, the text record, and the end record, right? So hope you know this, or we'll just take a dive into it. So header. So the first column, we'll refer to it as columns, right? We don't use bits, gets, and all of that for simplicity. Column. So the first column contains h, that's h, and the next 2 to 7 right here will have your program name. You can see your program name right here is sum, right? So this thing you will fill it right here, SUM, and the next 3 spaces are blank. We'll have this caret symbol, and then your next value comes into play. So 8 to 13. So 8 to 13 will have starting address of the object program. So starting address, you can see this is your starting address, right? And it's 3 3. So this is 4 right here. How do I fill? So basically you fill in 2 zeros right here, and there you go, you fill in the space 0 0 3 0 0 0. So that's our starting address. And what is this, right? So columns 14 to 19, what do? They are nothing but the length of the object program, that too in bytes, and then we'll convert them into hex, and that representation is what this is. So we'll get to this. So how do we do this, right? How do we do it? So that is why I said write the starting address right here. So what you do is you take this value and subtract it with this value. You basically get your size or your length, that is 178B. So there you go. And that thing you fill it right here. Next, moving ahead, we have our text records. So text records will hold all the object code right here in them. So the first column is TS. We put in the T right here. This is your first column. So again, next, what do? Starting address of object code in this record. So we put, this is from 2 to 7. So starting address. So here in this text record right here, the starting address is the same as this thing, the program 00 and your 3000. That is your starting address. And next, what is this? 15, 15. It's not 15, it's 15. Now, this is the starting address. Okay, this was the starting address, right? And this will get to it. This is nothing but the length of object code in this record in bytes. So we'll get to it. It's column 8 and 9. So how do we do this, right? We'll get to it. Now you can see from here you start putting in your object code. So B410, B410, and then a caret symbol. And the next record, the next code, 0, 1, and all your zeros. That's this thing. And then you go next, you put a caret symbol, and then 6, 9. You do that until you reach your end. And wait, you don't just fill in all of it. It takes this value takes 10 to 69. So there is not 69 here, but we have 69 places to fill. So if it exceeds 69, we can take another text record and start doing the same. We're changing the starting address of that text record, and yeah, you can carry on. But for now, our object code is fitting into one text record. It's fitting under 69 columns, right? It's going right here. So this is the length of how much code there is right here. How do we calculate that? I'll tell you. So basically you need to know 2 columns right here. 2 columns takes up 1 byte. I'll write it right here, 1 byte. Now, how do we calculate? So 4 right here. So 4 and then 10, because this is 6, 10, 11, 12, 13, 14, 15, 16, 17, 18, 18, 18 plus 6 again, I guess. 6 is 24. 24 plus 6 again is 30. 30 plus 6, I believe, yeah, 6 is 36. And 36 plus 6 is 42. So we are using 42 columns right here, right? We're not using more than 42. We're just using 42. We have more space left in this text record. So 42, they have 42 columns, right? As you can see, 42 columns. And then 2 columns take 1 byte. So 42 columns takes 21 bytes. Known, obviously. I said that 2 columns is 1 byte. So now 21 bytes of memory it takes. So this in decimal, we need to convert to hex. So 21, if you convert into hex, what do you get? You get 15. So that 15 is exactly what this represents right here. I said, right, this thing. Yeah, the length. Now moving ahead, we fit all our program into the text record, and now end record. We have our first column representing the E right here. That's done. And then a caret symbol. Now 2 to 7. Oops, on the line. Okay, 2 to 7. So what does 2 to 7 represent? So it's nothing but the address of the first executable instruction in the object program. You can see here, this is your first executable program or instruction, and that address is 3000, or should I say 3000, and that thing you'll fill it right here in the columns 2 to 7. Once you're done with that, your object program is complete. This is your object program. It's a bit dirty. Just clear it out. So these are your object program. Hope you understood. Thanks for watching. Please do subscribe.